Welcome to the Jack Westin MCAT podcast with your hosts, Michael Maleka
and Molly Hudash. Hello, everyone, and welcome back to another episode of the Jack Westin MCAT podcast with your hosts, Mike and Molly. This episode, we're going to be building on what we talked about last episode, which was MCAT math, which was so much fun to record.
Oh my goodness. It was so much fun to like talk about math and like talk about like all these things that we've done. We've seen all these things, right? And I hope everyone listening has checked out that episode. If you haven't, check it out. It was a whole lot of fun. We've talked about it so often in our trial sessions and when talking with students. So sharing on the podcast, I think, was a ton of fun. But today we're actually this is a content area that will really utilize those skills. I think when it comes to MCAT math, we're like, okay, math is important, but when do we use that math a lot is when we're doing problems around, a lot of times, things physics related. And we're talking about probably one of the most physicsy things on the MCAT. I don't know, like in terms of like connections to other physics areas, this is probably the most fundamental physics area of all the other ones, right? I think what we're talking about today definitely connects to every other area. So when a lot of people are struggling with like fluids or electrostatics or anything along those lines, even light optics, all these things, it all comes back to these core fundamentals which we're talking about today, which is forces, energy, and power. These are the foundations of physics, like those physics that we kind of like Newton built on, and then we built up from there, and then we apply them to all these other areas. So getting this strong foundation is so important and so critical to even applying it to the other things. So I'm excited because this is such an important class to talk about.
Yeah, and obviously there's a lot of math that we could use with this. We'll talk about equations, we'll talk about units, we'll hit on a lot of the things that we hit on last episode in terms of like what's important to know when doing math. We'll give you that background as well, but know that this material, yes, applies to pretty much like arguably every other physics concept that you learn on the MCAT and a lot of the biochemistry and the Gen Chem and the OChem.
Yes.
Like I really think that if keeping in mind that physics is the second smallest piece of the MCAT pie, so to speak, the second least questions come from physics out of everything on the MCAT. Only OChem is less than physics, or Orgo, if you call it that. With that in mind, I feel like if you were to pick one physics topic that you really, really learned, this is it. Like if you really learn this, I think that you could reason your way through at least like half of the 15 physics questions that will show up on your test. Like
it's that foundational.
It's that foundational.
Right, where even if they're asking something, it sounds like it's light, but it's really a lot of times it's just an energy problem. A lot of fluids. When we talked about fluids, one of the core fluids equations is just a conservation of energy equation. Sound, and that's related to power. Like all these things are just related, are applications of these core principles. So that's why I totally agree, Molly. Like a lot of these questions are just on this topic. So that's why I'm super excited to talk about it. And also, fun fact about me, I know you're all about evolutionary biology. I'm a huge physics nerd, like a giant physics nerd. Before I was even instructed the MCAT, I was a physics tutor. I instructed physics. And so when I teach these things, I've taught it in like a university sense, like for university classes, but also for the MCAT, I just like love it's because it's a lot of the same application, all of those skills. And also, good friends of mine are in like very high level physics, and so I love just listening to them. Like, wow, this is so cool. But again, all of those, it's so interesting when they talk to me about it because a lot of those things that they're talking about super high level, like astrophysics, relates to like energy and like forces and like power. So this is just that foundational to all of those things. So that's why I think I'm really excited for today. When we brought up that we were doing this today, I was like, oh, yes, I love physics. Cool.
Yes. And hopefully we can share some of that excitement and enthusiasm with you guys. I know probably at least a third of the people, the second we said physics, were like, oh,
right. Yeah.
Right. I was one of those people. I didn't have the strongest background from physics when I was in undergrad. I had 3 different physics professors, all of which only taught for 1 quarter. I was on the quarter system. I had an exchange professor. I had a brand new professor and a professor that was about to retire. I was scared of physics, but really it's not as bad as it might seem. Okay. So if you're feeling to yourself like, do I just skip this episode because physics scares me? lock in,
Quite the
right?
opposite. Quite
Lock
the
in,
opposite. This
buckle
is
up.
the
It's
episode
not
for
as
you.
bad as you think it is. And this is the one episode that you really need to listen
Mhm,
to if you're
mhm,
thinking to yourself, physics is not my friend.
mhm,
And really,
mhm,
also, this episode applies to everything, not just on the MCAT realm, but everything around you. Right.
mhm,
When we talk about forces and energy and power, this is the basics for how your body moves, right?
mhm,
How your food passes through your body
mhm.
also, right? How your muscles pull on your bones, how
Mhm.
you can open a door, right? Like there's so many
In the
layers to this
world, right?
that apply to the world around you. So super cool.
Yeah,
I
yeah,
say,
physics is so unique in that way. In on the
yeah.
MCAT, I'm sorry, I just had because all these other things that we study, like in chemistry and biochemistry, like we're like, oh, talking about mitochondria and like cells and nucleophilic electrophile. Like you can't actually see that happening. Like you can try to
Mhm.
visualize it, you can maybe get models, we can use analogies, but physics, you can actually see, you can actually experience, especially the stuff we're going to talk about today. Look around you. We're going to be using a lot of examples. I'm going to be doing a lot of pushing today on random things around me, right? And to learn these things, because physics is just such a unique area where you can put into practice the things that you're learning to actually see them.
Yes.
So sorry, I just so excited.
Okay, so let's start talking. I mean, we know we're going to talk about forces, we'll talk about energy, and we'll talk about power,
Hmm.
right? And part of this we'll talk about work and some other related
Sure.
concepts too, but let's start with the most foundational. Let's talk
Hmm.
about forces,
Hmm.
right? Forces, what are they? What do we need to know about
Hmm.
them? Give us the basics for someone
So
who's not heard of this before.
basics, basics, basics. So when it comes to force, I think it always is a good way to talk about it to start with units first. Like when you see a certain
Mhm.
unit, force is measured in what's called Newton. But what is a force? A
Mhm.
force is when you are, I guess conceptualizing a force is a little bit tough, but when you're pushing on something, when there is some sort of content and there is direction, where if you are pushing on something or something is being pushed against, there is a force. So, for example, right, I push on a wall. Therefore, I am applying a force. I am pushing on a desk. Therefore, I am applying a force. A conception that gets confused a lot, and we'll talk about where it applies, is a force requires motion. It does not require motion for there to be a force. A force is simply when something is pushing on something else. So,
Mhm.
for my chair, for example, my chair is pushing up on me. So therefore, it is applying a force. I am also pushing on my chair. I am applying a force to my chair. So all of these are different examples of forces. When I'm in water, I'm floating. The water is pushing up on me. So therefore, there is a force. The one place that this pushing, I like using the pushing idea. The one
Mhm.
place the pushing idea doesn't really apply well for is gravity, because
That's what I was
gravity doesn't
thinking.
push. So the reason is gravity is not actually a force, but for the MCAT, it is a force, but it really actually isn't. But the gravity is the one exception to the pushing rule, where it is also a force. For the MCAT at least. If anyone wants to talk Einstein, we can talk Einstein. But for the MCAT, gravity is a force and is the one exception for the pushing rule. Everything else, there's a push that's happening. There is something that is making contact and pushing against it.
Okay, right. So forces are pushing. It doesn't always mean I'm trying to push a dresser, right?
Yeah.
Again, like you said, it's some things that we don't even notice, right? We'll talk about Newton's laws, right?
Mhm.
That you don't think the chair is pushing up on you. It's not like
Mhm.
there's someone underneath your chair shoving it
Right.
up towards,
Mhm.
your bottom, right? That's
Mhm.
not
Mhm.
hopefully that's not happening. That would be
You
a
don't know what's
weird
under this chair.
situation.
You don't
But there are forces all around you that you don't even think about, right?
Mhm.
Because again, forces individually do not always create motion. What
Mhm.
you're hinting at
Mhm.
is an idea of a net force. Because
Mhm.
ultimately, you could have a million forces acting on you at once. You might stay motionless. To define force in terms of an equation, which I feel
Mhm.
like is sometimes helpful, and I feel
Mhm.
like it's also helpful to talk about gravity, even though,
Mhm.
according to you and your physics brain, gravity is not a force. It is for
For
the
the
MCAT.
MCAT, it's a force. For
It
the
is for,
MCAT, it is a force.
yes.
I want to preface it. But
So
okay. Sorry, continue, continue,
Mike,
continue.
our designated physicist, is
Yeah.
upset about this.
Mhm.
We want you to get the highest score possible. We're going to talk about MCAT stuff.
MCAT. Mhm.
We'll let Mike ramble off screen later.
Sure. Mhm.
When we talk about forces, we should really talk about the person who discovered all this stuff, right? So we talk about Newton. You might have heard the story of sitting under the apple tree and the
Right.
apple falls down, and oh my gosh, there's an epiphany,
Mhm.
right? Of the three different laws of motion. When I talk about an equation for force, I'm really talking about the second law, right? Which
Mhm.
is quantifying force, but
Mhm.
I think it's helpful to go in chronological order or in numerical order. Let's start with Newton's first law,
First law, right.
right? Rather than go straight to quantifying, right? The idea is if you basically you want to continue doing what you're doing.
Mhm.
All right. If you are not moving,
Mhm.
you are not just going to suddenly move with no force applied. Like you're not
Mhm.
just going to suddenly acquire
Mhm.
movement.
Mhm.
Okay. Because to do so would require you to accelerate from rest to do something.
Mhm.
We'll talk about acceleration in a second. That is
Mhm.
something that we see with forces, right?
Mhm.
Or can see with forces. So if you are motionless, if you are at rest, you're going to stay at rest, right?
Mhm.
If you are in motion,
Mhm.
you are going to remain in motion
Mhm.
unless a force acts to stop you.
Mhm.
You might think to yourself, if I kick a soccer ball,
It doesn't
it
go
does
on
not
forever.
just continue forever. Like that's what
That would be pretty
Newton's
cool.
first law
Yeah.
sounds like. An
Mhm.
object in motion is going to stay in motion.
Mhm.
No, no, that's not how that works, right? Of course,
Mhm.
we've seen that happen,
Mhm.
right? It's will remain in motion unless acted upon by an external force, right?
Mhm.
And you might not see anyone pushing on that soccer ball,
Mhm.
but know that that soccer ball is experiencing air resistance. It's
Mhm.
experiencing friction if it's
Mhm.
contacting the grass. It's
Mhm.
rolling itself,
Mhm.
right? It's experiencing gravity.
Mhm.
There are a million forces that we experience, right, in the world
Mhm.
around us. So
Mhm.
Newton's first law, if you are at rest, you will remain at rest
Mhm.
unless a force acts upon you. And if you are in motion, you will remain in motion unless
Mhm.
a force acts upon you.
Right.
That's the basic
Basic
idea.
idea. Mhm.
There are forces everywhere, though. So
Yeah.
this is not, perpetual motion. This is not
I
just
found
something that
infinite
will.
energy, a great way to like conceptualize like, oh, where is this applied? Think about a place where there is no forces, like
Mhm.
in
Like
space,
space.
right? Like say if you were in the middle of space and you push something, like you like throw a ball in space, it's not just going to stop. It will
Yep.
go on forever. Right? That's I
Mhm.
think the one of the kind of like because we can conceptualize we've all seen Interstellar, like what happens there, like in
Yeah, and
space.
Gravity
Yeah,
too. That
right.
movie. They came out
As
at the same time.
oh, I to be honest, I haven't seen Gravity. I have seen Interstellar
Oh,
though.
it's good. It's
Oh,
good.
really? Right. But you can conceptualize. That's a great application of Newton's first law, where yeah, object. If you put that ball in motion, it will go on forever because there is no external forces in space because there's nothing in space. It's a
The
vacuum. That's why
vacuum.
you
Yeah.
can't exactly apply it on Earth because there's air molecules that cause air resistance and friction on the ground. So that's where a good application of Newton's first law is. An object in motion will stay in motion. That is the first law. But then
Yes.
we talk about the second law. What is the
Mhm.
second law? It's the equation, like you talked about before, where the net force equals mass times acceleration. That is Newton's second law. Now, notice our stress on net force equals mass times
Yes.
acceleration. Because that's what Newton's all about. Because if an object does not have any net forces on it. Now, what do we mean by net force? If I add up all the forces on an object together, right? Like take me for example. I, right now, am not accelerating in any direction. It would be pretty bad if I
Mhm.
was, right? But that doesn't mean there are no forces on me.
Mhm.
There's a force of gravity on me, which for the MCAT
Mhm.
is a force, if you know that. There's the chair pushing up on me. It's pushing up on me, so there is a force from the chair. Just because I'm not accelerating does not mean I have zero forces, but the issue is the net force is zero. That's why I'm not accelerating. Because my force of gravity is exactly the same as the chair pushing up on me, the normal force, which we'll talk about in third law. Um, where because they are the same magnitude, and they're in opposite directions, they'll completely cancel out, right? And therefore, because they cancel out, there is no net force. Net just means when you add up all the forces, what is the net force, right? When you add them up, what's the product? So if the net force is equal, there will be no acceleration. But that's what's really important. If an object does have a net force, the forces do not balance out, then you must, by law, according to Newton's second law, you must have an acceleration. And this idea is so core to every forces, every torque problem as well. Like that torque is a little bit of a
Yeah.
different, is so core. The first questions you should ever be asking yourself is there a net force? Is it
Yes.
accelerating? Because if it is accelerating, you know for a fact there must be a net force. If there is a net force, you know for a fact there must be acceleration. And so that's
Yeah.
one of like those foundational things where, okay, then there is net force equals ma.
Yeah. And I
Mhm.
feel like it's also really important to explain what acceleration is,
Sure.
right? I mean, you all know accelerate in a car, it means you're starting to speed up, right? Acceleration is a change in your velocity, right? You're
Hmm.
going faster is acceleration. When we say F equals ma, though, deceleration is also fine, right?
Yes.
Acceleration means that your velocity is changing.
Hmm.
And this, I think, this clarification brings up something really important
Mm.
because if I am, let's say I'm in space, right? Someone has pushed me,
Yes.
right? Or I've thrown something and now this object is moving. And let's
Mm.
say it was moving at 10 meters per second.
Mhm.
And maybe it had to speed up to that, but now we're at 10 meters per second and it's staying 10 meters per second and it's
Mhm.
staying 10 meters per second. There's no change in velocity.
Mhm.
Do I have acceleration or deceleration in that case?
Absolutely not.
So do I have a force?
Not a net force.
Yeah. So if F equals ma,
Hmm.
right? And this is the equation for the net force, which is super nice. Again, if you have an object changing velocity, if you have an object that's accelerating or decelerating, you have a net force,
Hmm.
right? If you do not have velocity changing, either because you're at rest or because you're moving at
Hmm.
constant velocity, your net force is zero,
Hmm.
right? And this becomes really important when we talk about free body diagrams, which we'll talk
Hmm.
about in probably a couple minutes. But like the idea is it's a diagram that you've got all of the different forces acting upon you that
Hmm.
are kind of coming off your body or applying
Sure.
to your body, right? And you're trying to figure out how am I going to move? If I am squeezed from all directions, or if I'm pushed to the left at the same time that I'm pushing down and something's pushing up on me, how am I going to move?
Hmm.
That's how we figure out net force. Again, if
Hmm.
I'm moving, I've got one. In your example, right, you are not accelerating.
Hmm.
You are pushing down on the chair like the chair is pushing up on you
Hmm.
in response, the normal force.
Hmm.
But if someone came over and pushed you a little bit to the left, you
Hmm.
don't have anything to the left of you that's going to push you right back and keep you stable. If
Hmm.
someone comes over and gives you a little push,
Hmm.
you will move. You will accelerate from rest, right? Because there will be a net force in that case,
Right.
right?
Right.
And the fact that we can use that F equals ma equation is very
Hmm.
useful. And
Hmm.
to think about a Newton, right? Forces are in Newtons. Keep in mind, mass is m, right? Acceleration is a. You'll see this a lot of times with gravity. F
Hmm.
equals mg. G is the acceleration due to gravity. The units, mass is kilograms, right?
Hmm.
That's the SI unit standard. Acceleration, whether it's A or G, which is just
Hmm.
specifically for gravity, is going to be in meters per second
Hmm.
squared.
Hmm.
Okay. If it's F equals mg, the constant that you want to be familiar with is 9.8 meters per second squared, or just 10.
Just 10. For the MCAT,
Just
it's
10.
10. Don't worry
Okay.
about 9 point.
So if you wanted to
Hmm.
do, quickly, what is the force of gravity? Force of gravity on an object that is 5 kilograms. Okay. F equals m, which is 5 kilograms, times g, since this is acceleration due to gravity, which is 10 meters per
Hmm.
second squared. So if it's 5 times 10, it's just 50,
Hmm.
right? That's it.
Great.
So just so
Amazing.
you know, with the math, you see this all the time with
Hmm.
forces.
Hmm.
It's very simple math. You just have to figure out, are we talking about an individual force? Are we talking about a net force? And
Hmm.
how is the object moving? Or how is
Hmm.
whatever has mass? How
Right.
is it moving?
How is
What's
it
going on
moving?
with it?
Yeah. Is it changing velocity? Is it not changing velocity? A lot, yeah. And I think you really hit that distinction against between acceleration and velocity really well, where a lot of times I hear people say, oh, it's moving, therefore it's a net force. Like, no, no,
Yes.
no, no.
Mm-mm.
No, 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 no. No. It could be moving, but if it's a constant speed, that means there is no net
There
force because
is
there's
no
no
net force.
acceleration. Right. And
Yeah.
so I think that term constant speed comes actually up a lot. Like in problems, they're
Mhm.
like, oh, how do we keep it moving at a constant speed? Net force is zero. Acceleration is zero. That should be like the first, like when I have students who read questions and they see constant speed, I'm like, highlight that's so important. Okay, that's where you should be starting kind of deal. So yes, please, anyone listening, do not, please make sure to, oh, how do I word this? Don't, how am I going to word this? I'm having a hard time wording this. Don't mix up acceleration and velocity. Those are very distinct, should be very distinct things in your mind.
Hmm.
Cool. And I think now we can actually chat about free body diagrams because how do we study this? Because we know there's so many forces that can act on a single object. Oh, actually, did I talk about third law? I don't think I talked about third
But
law.
it's related, so
It's
you can
related.
use them.
It's related, right? So actually, maybe let me sit back and talk about third law. I'm just so excited to talk about free body diagrams, but we should talk about third law. Third law, we've talked about first law, which is an object in motion will stay in motion. Second law, net force equals ma. Third law is one that we've probably all heard before, but I don't think a lot of people actually conceptualize.
I
Um,
had no idea what this meant, even though I
uh,
had it memorized. For many years, I did not know this.
I was honestly the exact same. It's every action has an equal and opposite reaction, or in maybe MCAT terms, every force has an equal and opposite reactive force. And now these are the terms that are very important. Equal and opposite. Every single force that is out there, every single force that is present, there is no exception to this. There is another force that is equal yet in the opposite direction.
Yes.
Now, I think it's really important to help understand the third law. We give examples of this. Right? I think the examples is what really helped it click in my mind. And so I'm gonna just push on the wall behind me. Anyone listening, I'm pushing on a wall right now, on a wall behind me. And when I
Oh my
push,
God, the entire house
oh
moved.
my gosh, what? No, I'm just that jacked. But when I push on this wall, I'm applying a force. I'm applying a force to the wall. Yet, my hand is not really moving. It's not
Hmm.
going anywhere. So that means there's something stopping my hand. And because I'm applying a force, there must be some reactive force, some equal and opposite force. And in this case, from my hand pushing on the wall, the equal and opposite force is the wall pushing back on me with the exact same magnitude in the exact opposite direction. So this idea where every force is an equal and opposite reactive force is so critical and something always to keep in mind with the equal and opposite reactive forces, they will never ever both be on the same object, right?
Hmm.
This is something that is so critical. You will never have reactive forces on the same object. Never, ever, ever. There's like a key example where people think these are the reactive forces, but they are not. And we'll talk about it when we get to free body diagrams. But they're never on the same object. I'm applying a force to the wall. The wall is applying a force to my hand, right? Another example. I'm applying a force to my chair right now. Therefore, my chair is applying an equal and opposite reactive force to my body. The forces are equal and opposite, but on different objects. They will never, ever, ever be on the same object. The place where we see a lot of the times people mistake the equal and opposite reactive forces when we talk about free body diagrams, when we talk about the normal force and the force of gravity. A lot of people think that these are reactive forces because, right? Are they not equal and opposite in many cases, Molly?
In your chair,
Yeah,
right?
right. There, that seems like the case where I have the force of gravity on me and in the equal and opposite direction because I'm not accelerating, the normal force is up on me. So are those not reactive forces? And the
Those
answer,
would be.
the force of gravity and the normal force?
Well, they're not equivalent in magnitude in all cases. In
No,
that
no,
case, they're
okay.
equivalent in magnitude. That's what I thought you were asking.
Oh, no, no, no. They're equal in magnitude, yes.
Yeah.
Okay. But they are not, by Newton's third law, reactive forces.
Yes.
Yeah, I was like, wait a minute.
I
No,
was
no,
like, they are equal in magnitude.
they're equal in magnitude, but they are not reactive forces according to third law because they are on the same object, which is me, right? So to the force that I'm applying to the chair, the opposite force, the reactive force, is the normal force. This normal force is, we see it all the time. That is the reactive force. When you see the force of normal of a block on a surface, the force of normal is the reactive force of the block pushing down. Yeah, if the
Mhm.
force of gravity isn't the reactive force of the normal force, okay, I know that reactive force is the force of the chair, me on the chair, and that's the force of the chair. But then what must be the reactive force of the force of gravity? Every force is an equal and opposite. So if the normal force is the chair force, what's the equal opposite of the force of gravity then?
It would be us. Well, it's us being pulled down to the earth and the earth pushing back on us.
Right. So our opposite force is us. Yeah, because the force of gravity is the earth pulling down on us.
We're
But
pulling the earth up.
we're pulling the earth up. That's such a crazy. I remember when I like learned this the first time. I was like, wait a minute, I'm pulling up on the earth?
Mhm.
Yeah, we all are. That's the idea of gravity. Everything with mass pulls other things with mass. You and I, Molly, have a force of gravity. Anyone listening has a force of gravity, and the force of gravity is infinite. So I am technically, with my mass, pulling Molly right now, who is in California, and I'm in Canada,
Canada.
right? But we don't feel it because it's just so minuscule and small. But the reactive force of the force of gravity is not the normal force. The reactive force of the force of gravity on us is us pulling up with our force of gravity on the Earth, right?
So cool.
Isn't it? Isn't it? I don't know how rambly or how much sense I just made, but I just think it's so cool when thinking about reactive force is us pulling up on the Earth.
Yeah. And
Yeah.
I feel like what gets really confusing, like I think when objects are not moving or accelerating, people at least can try and conceptualize like, okay, maybe we're not getting reactive forces exactly right, but you kind of understand logically there's no acceleration. It's important to know the difference between reactive forces, but like, okay, I'm not moving, there's no force. Or
Mm,
there's no net force, I should say.
mhm,
What I think it's really confusing is when we start to add in other variables. Like, what
mm,
if you are experiencing a net force, but
mhm.
you still have gravity to contend with? You still have the normal force to contend with, as well as their reactive forces, respectively. Like, for example, and I want to hear your rant about this because I could tell you're going to be really excited about this. What happens in an elevator?
Okay, cool. I was like, what is she on about? Yes, cool. So, so very, very cool that you talk about this because when we have an object, right? Imagine ourselves in an elevator, right? I can
Mhm.
imagine myself in an elevator. Say the elevator is still, my force of gravity is on me. It's mass times gravity. It's not changing. My force is normal because I'm pushing down on the floor is pushing up on me. But I'm not accelerating, no change. However, we can imagine we've all been in an elevator before, right? And it starts
Mhm.
going upwards. We begin to accelerate. What feeling do you have when you begin to accelerate upwards?
Like you're being pulled, like your body's trying to stay where it originally
Right,
was.
it is. When I start going, I feel like, oh my, I feel so heavy. Like imagine
Yeah.
if we went, like imagine if we went up really, really fast. You would feel so heavy. In the same way,
Heavy.
when
Yeah.
you can imagine when you go down really fast in an elevator, like accelerate really fast,
Light.
you feel like really light. But
Hmm.
now these are interesting because is your
Hmm.
weight actually changing in those two cases?
No, of
No, right?
course
Your
not.
mass isn't changing, your gravity isn't changing, so your FG didn't change at all. Yet
Hmm.
I was accelerating in both cases. I was accelerating up and I was accelerating downwards. Therefore, there must be a force that is changing in order to mean that I have a net force. And in both those cases, it was the normal force, right? In the
Hmm.
first case where I was accelerating upwards, well, if the normal force is pointing up and the force of gravity is pointing down, because I'm accelerating upwards, I must have a net force that is upwards.
Yeah.
So the only force pointing in that direction is my normal force. So that has to get larger, right? This is actually our feeling of weight is not from the force of gravity. It's from the normal force. Your normal force is your feeling of weight. That's why you feel heavier when you go up in an elevator because your normal force got larger. You didn't actually get heavier, but your normal force got larger, therefore you felt heavier. In the same
Hmm.
way, when you go downwards in an elevator, you start accelerating downwards, you feel lighter. Well, your mass didn't actually change, right? You're still the same mass,
Hmm.
so your FG didn't change, but your normal force, because that's the one that can change, because there's a net force downward, the normal force had to get smaller. So there's a net force downwards. So because the normal force had to get smaller, that's why you felt lighter, because the
Yeah.
normal force was smaller. So I just think your actual feeling of weight being the normal force is so cool.
Yeah. I love that. I love that so much. And I remember so distinctly, again, when I was first starting my studying, I felt like I had, mountains to move, so to
Hmm
speak,
hmm
with physics. Like I just felt so unprepared for it and I had really had to learn it. I remember when I learned it, I learned exactly what you said was not true, which is that normal force is the reactionary force to gravity. Like that's, oh, well, when I'm at rest, those are equal and opposite. Like the values are equal and opposite, sure, but they are not reactionary forces. Like that is not, they're not opposing. And so when I got to elevator problems, I was like, okay, well, I know my weight doesn't change. And the normal force is always equivalent to my weight. And I
Right?
remember missing my first question and I was like, what the heck?
Right?
Like, what do you mean? What do you mean? And I had to unravel that whole thing and then put it all back together. So thank you for summarizing that for those of us who have had experiences of shock in that case of like, wait a minute, hold on,
FN can
pause the
change.
tape.
Yes.
What is
Yeah.
going
What
on?
is I feel cheated. Yes,
Yeah,
FN does
the
not have to be
record
constant.
scratch. Yeah. Yeah. I think
Uh,
the elevator is such a classic example, and I've seen so many different variations
mhm.
of it. You will see it. Well, I can't guarantee you'll see it on your test, but
Right.
it's so common. And that can be a discrete question too.
Hmm.
It could be a passage, but it's also very easily packaged up in a calculation question with the free body diagram, which again is just like you could draw an elevator and you could draw the downward force of gravity. You could determine the net force of if it's going up or down. You'd have to figure out the normal force because again, those should all equal, right? The net force should equal to your mass times your acceleration, right? They might ask you to calculate acceleration given the other forces, in which case you'd have to figure out what the net force is and your mass and solve for acceleration. They could do it in a lot of different ways, but it's pretty classic. That's a major way that they will test this. Although,
Right.
again, they love to test this in other ways too. I feel like it'd be useful to give a couple other examples. Like, if you want to mess with F equals ma, elevator is classic, but,
Right.
even like objects that slow your acceleration, decrease
Mm.
the force. Like a common example is airbags. Why does an airbag in a car help you? Right. And in fact, they can cause injury if they come out too fast and you're close, it's smacking you in the face. Like, how does that help me? When they're fully inflated and then you're moving towards it and you don't have an airbag, all of that force is going to smack against your steering wheel. We'll talk about pressure as well, but pressure is force over area. If your head hits a narrow little steering wheel, that's an incredible amount of pressure and you can crack your skull, right?
Right.
Or have a severe head injury. The thing with an airbag is it's coming a lot closer to you and it's got some give. It's also very wide, right? So ultimately, if we think pressure, your same amount of forward force from the accident is spread out over a much larger area. You don't have as much pressure that could really damage your brain and your skull, but also it's slowing you down. It's actually decreasing your acceleration forwards towards the front of your car, and that is decreasing the force of the impact, which can also help protect your cranium,
That
right?
cranium, that big old brain
Which
filled
is
with all
why
this
cars have
physics
airbags.
knowledge. Yeah, yeah.
Yeah. I'll take a black eye over brain damage, right? Like
I
it's
any day of the week. Any day of the
right. Like
week.
keep your airbags ready for deployment if you need it, right?
Right, right. And that's just one great example of like why some things happen. I mean, that's also applicable for like, when we like trampolines, right? Like if you fall from a larger
Mhm.
height, that trampoline like slows you down, right? So therefore the force that you generate is not as large.
Oh,
So stuff like that. It's
oh, that's fun. Now I want to talk energy so bad.
Okay, okay, we
Kinetic
will
and
talk energy.
potential. I
We
know,
will
I
talk
know.
energy. We will talk energy. Another great way, especially a biological example of like forces, because there are also plenty of forces, like the way our musculoskeletal system moves. Like, how do
Lump and
we
iron.
actually move, right? Because really, if you really like to strip down like the human being, we're just a whole bunch of bones and meat, right? Like,
Mhm.
but the MSK system, the musculoskeletal system, there's a reason those two are named in the same word in the same system because it is our muscles that generate a force on our bones. They're insert onto our bones. There's like two inserts, right? One on one bone, one on another, and by contracting, they apply a force to our bones, and that's why we can move. Every movement that human beings can do is just because a muscle pulled on some bone or some tissue, and like that's why I can move and I can do all these things because there's forces generated by muscles.
Yeah.
Mhm.
So cool. I
Mhm.
love that. It's forces in particular, forces and energy. I mean, all the stuff we're talking about, it's everywhere. It's also the reason you're not constantly falling down. Like the
So
difference,
true. That would
the
be
difference,
pretty bad.
in Canada, walking on ice
Yeah.
versus walking on the ground. Like there are even differences with forces in that of
Mm.
friction. Friction is a
Friction
force.
forces. Yeah, yeah.
Like that's critical to understand too. And there's so many different layers to this. There are so many different types of forces that we could get into. Again, gravity is an important one to know. And it's in that case, if we're talking about the force of gravity, the equation that the AMC will use is the same, F equals ma. But rather than acceleration that could have any value, the acceleration due to gravity is 10 meters per second squared, right? So that's the gravity equation. Not anything super new. It's just a constant to know. 10 is not too bad. Makes
Yeah.
the math pretty easy,
And I feel like
right?
many of us have like heard that, like if they've taken
Yeah.
any physics, it's like, oh, you remember 9.1. Like it's kind of like Avogadro's number. It's like 6.2 times 10 to the 23.
Yeah,
Like it's one
yeah,
of those numbers that you just, I was seared in my brain at least when I was in,
yeah.
I think, high school. Yeah.
And
Um,
because MCAT math, as we've talked about, is so flexible with the fact that you just have to pick the right answer out of 4, 10. Just say 10.
just say
I've
10.
never
Just
seen
say
a
10.
time where you need the exact number. Just do 10.
Me neither.
Okay.
Me neither.
They will even tell you sometimes if
10.
you are lucky enough to get the constant in a question from the AMC, they'll tell you 10.
Yeah.
Like it's
Yeah.
just do it.
Mhm.
Right. We talked about normal force, which
Mhm.
we've actually talked a lot about normal force
Mhm.
already, so we don't need to define that again,
Mhm. Mhm.
right? That's not just equivalent to your gravity in reverse,
It's
right?
not.
We've got friction, friction of moving objects,
Mhm.
right? And friction of objects that are not in motion, right?
Mhm.
Static friction, if I'm pushing on something that's not moving, and kinetic friction. If I want to get, let's say, a really heavy dresser to move, I'm going to need to push on it for a
Mhm.
while,
Mhm.
and I might struggle for a while and then finally get
Get
a
it.
little bit more
Finally move.
force, a little bit more, and now it'll start to slide, right? I
Mhm.
have friction that's essentially pushing back against my motion while I'm struggling for it. If
Mhm.
I can muster a little bit more force, I might be able to get the object moving a little bit. But as we know, right, if I got a really heavy dresser moving, because there are lots of other forces going on, it's not going to just keep moving that forever,
Forever and
right?
ever. Yeah.
And even in that case, kinetic friction exists as well. So there's even still friction when it's in motion.
Mhm.
Um, yeah, and if we're talking about pushing something from rest that then becomes able to accelerate or have velocity in a particular direction, you got to consider both. So
Mhm.
static and kinetic friction is also something to keep in mind.
Mhm.
And conceptually, if I have to work,
So
basically
much harder.
it's much easier once I get it moving. I can
Mhm.
probably get what I need done. Um, it's much easier to continue something's motion than to start it from stopping. So the when we talk about friction, which we probably won't get into in too much more detail than this, the coefficient of static friction is really high,
Yeah.
more
Much
than
higher
it
than kinetic. Yeah.
yeah, more than kinetic.
Mhm.
Again, it's harder to get something to move from stop or from, rest than to continue something's motion opposing
Yeah.
that kinetic friction.
Absolutely.
Um, what other kind of forces do we have?
Oh, we got so many forces. I
I
mean,
know.
we've got tension forces. So like imagine when you are like pulling on a rope, right? Or you have a string pulling up on something,
Or an
uh,
elevator shaft.
or an elevator, a string pulling up on an elevator, right? Those are all tension forces. Now, for the MCAT, there is no force of tension equation that you need to know, but a lot of the times you'll be expected to be able to find the force of tension using our net force rules. So,
Yeah.
like a lot of the times when we have a force of tension, the net force is zero. So, whatever's balancing it out, it'll be equal to. So, those are some kind of like applications of the force of tension, but there is no force of tension equation that you need to know. But
Mhm.
whenever there's a rope, it's a tension force. But there's also a spring force, right? And
Yeah.
there's kind of a lot of cool applications. I just like think, imagine you have a spring up against a wall, right? The spring up against the wall, it's just sitting there, nothing's happening. But as soon as you push in on the spring, you kind of compress the spring, you can feel it. It's pushing back on you, right?
Yeah.
And we can calculate the magnitude of that force as pushing back on you. And it's a really small equation, right? It's F equals kx. You'll see a negative there a lot of the times, but a lot of the times negative just refers to direction. So I just like thinking of it as F equals kx, where k represents it's like like the spring coefficient, which is
Yeah.
kind of like how hard is it to compress. That's what k represents. Like so you can imagine like a spring on a car really hard to compress, whereas like a spring like a slinky spring.
A slinky. Yeah.
Yeah, slings been super easy to compress. So very low K coefficient. Um, and X represents from the kind of neutral position, what distance, it's a meters, what distance have you compressed it, right?
Hmm.
And so that's where F equals Kx is the the spring force equation. If you want to calculate the spring force, you multiply the K by X. They will give you K. You don't need to memorize any K constants when it comes to springs, at least.
Yeah.
And yeah, so that the spring force is another one, and also when you have like elastic bands are another example of like the spring force, where when you pull on an elastic band, you can feel the force. Exact same idea. The
Mhm.
application is a little bit tougher, so normally you'll see it just with the classical springs, but that's
Yeah.
another application of spring force.
Yeah. And
Mhm,
so we've talked about so many forces. I feel like you guys are probably tired of hearing forces because you can never get tired of forces. They're literally everywhere. What
mhm,
we've been describing though are all very linear forces.
mhm.
Uh, know that there are also rotational forces, which
The
we are not going to
rotational
touch
world.
in this episode, like torque. There's a
Mm,
lot of applications to what we call simple machines here,
mm,
right? Like a pulley or a inclined plane and all
mhm,
these things. The wheel that you can learn about, and it's pretty cool. They're all applications of this same content of forces and energy. We're not going to touch rotational forces or rotational equilibrium in this episode because we simply do not have the time, but that's
mhm,
also something that you might see related. Um,
mhm.
and on that note, I feel like we're ready to talk about my favorite thing,
Oh,
which
amazing.
is
I'm ready. We
energy.
love energy, and we're just drinking energy drinks as we're talking about it. You
I
knew I was
know.
gonna make that joke.
Mhm. It's what
Yeah.
I constantly have way too much of.
I am jittery at the moment. If
Yes.
I was a little scatterbrained earlier, you now all know why.
Yes. And I feel like for someone like me that feels like I always have energy pouring out of every pore, it feels like I am just my own generator. Like I
Mm,
just create energy out of nowhere. Is that possible? Can I create energy out of nowhere?
absolutely not. That is one of our laws of
Absolutely not.
thermodynamics, right? Energy cannot be created, it cannot be destroyed, right? Although, while Molly seems like a wellspring of an energy creation, she doesn't. She's actually stolen it from something else.
Mhm. Yes, I'm an energy thief.
Ah.
Steal from the rich, give to the poor, right?
And the energy Robin Hood,
I am the
one might
Peter
say.
Pan of energy.
Peter Pan? You mean Robin Hood?
Yes, not Peter Pan.
I'm like Peter Pan. Nice.
Yes, Robin Hood, thank you.
Yeah.
That is hilarious. Yes, that's the conservation of energy, right? The idea here that's very applicable to a lot of different contexts is that energy is never created or destroyed. It's simply converted between different forms. You may hear of processes that are inefficient, right? Even like muscular processes, right? There are things that go on in our body that are not perfect of, let's say, certain types of potential energy being converted into kinetic energy, right? Which is movement. Sometimes those processes aren't perfect. And sometimes energy, and I'm doing this in air quotes if you're listening, is lost. Okay. We hear that a lot. Oh, energy is lost. That's not an exception to conservation of energy. Okay. We
We didn't
never create
destroy
or
it.
destroy it. No, no, it's not destroyed. It's released as heat. Okay. So
Mm,
most of the energy that we quote unquote lose with processes that go on in our body that are not totally efficient, this is heat loss. And it's the reason, right? If you think of going to the gym, which I know we both like to do, or running, like
oh, no, I
neither
don't
of
do
us
that
like
one.
to do.
I don't do that one.
Any sort of muscle contraction and activity, you release heat, right? You get hot, you get sweaty. It's because muscular contraction is not a perfect process. It's also why we've talked about uncouplers a long time ago.
I was thinking that as you were talking about it.
Mitochondrial uncouplers. This is all the way back when we were talking about
Metabolism.
metabolism.
Mhm,
There are these drugs, right? And other types of toxins and things, but drugs that basically unhitch ATP synthesis from the electron transport chain. And instead of harnessing the energy released from the electron transport chain to make ATP, which basically we're taking that energy that potential energy and we're storing it in a new chemical bond, right? Instead of doing that, which is conversion of energy, we let all that energy go as heat, right? Those uncoupling agents actually used to be used as a weight loss drug and have since been banned for many reasons, but also
very dangerous.
if you took them, you would literally cook your body from the inside out because all of that energy is quote unquote lost, but it's never actually lost. It's released as heat. That's a not very, it's seen as not a very useful form of energy in most systems, although we could talk about how we can do steam power and whatever else, but
yeah,
it's
kind of.
pretty much useless. Okay.
It's and this idea of the use of energy is really cool because there's a core assumption with conservation of energy that there is a finite amount of energy in the universe. You can't create or destroy any. There's just a finite amount. But right now it's in useful ways. But like there's a theory called the heat death of the universe, right? Which I think is cool. Where it's like we only have a finite amount of energy. There is no perfect conversion system in the world. While we a lot of times with the MCAT we say, oh, it's completely converted, like not really, right?
Yeah.
Like where we every system loses a little bit of heat, where eventually after enough times, enough reactions, like eventually there will be no more useful energy left. All of the energy will have been converted to a not useful form, like heat. So if we run out of energy in the universe just dies. Like there's nothing. And so that's if anyone's
Wow.
ever heard of the heat death of the universe, it's like when all the useful energy that we can actually harness is converted, not lost, like as in destroyed, but just converted to a not useful form, which is heat.
I love your just pervasive optimism.
I
So
love it's like I'm just
optimistic.
like
You
so
always really,
yeah,
it's
hey,
such a
want to hear about the
feel-good concept you're bringing.
want to hear about the heat death of the universe? Don't worry, that's like billions of years away. Like we are that's so far away. But hey, cool application of conservation of energy. You're not losing. None of it's destroyed. It's just being converted to
Yes.
heat.
Yes. So in talking about energy, I think for me, the classical example that I always learned about with energy, especially when we break it into the major classes of potential energy and kinetic energy, to me, the most clear indication of this, especially when we talk about mechanical energy, is like a ball rolling down a hill,
Sure.
right? You've got a ball sitting on top
Hmm.
of a very tall hill,
Sure.
right? Imagine, or a slinky,
Oh,
slinky on top
interesting.
of a staircase, right? Who cares?
Oh, gotcha. I was like Slinky on a hill. That's
No, no, no. That wouldn't work. Slinky on a staircase. So because we've got this ball situated all the way at the top of this hill, what we experience, right, due to that force of gravity, we have energy created, right? We are suspending this object up far away from where it truly wants to be. Right? Again, the earth is pulling down on it. It is storing energy in its position in this elevated area, right? So at the top of the hill, it has what we call potential energy. And in this case, it's gravitational potential energy. It's not in motion, okay? No acceleration, no velocity, nothing, okay? It's just sitting there. We could calculate the amount of energy which is stored or is measured in joules, right? And we'll talk about joules actually. I feel like we should get the basics in, right? In order to understand this, gravitational potential energy is very literally the force of gravity that pulls down. Okay, so mass times the gravitational acceleration times how high up it is. Okay, so if you can imagine, we have an energy value or an energy variable that is equal to m times g, which is a force, times height. Okay, if we thought about the units, m times g is a newton, right? It's a kilogram times meter divided by second squared. If we're multiplying this by a unit of distance, we basically have a newton times a meter. A newton meter is a joule, okay? This will also help us understand an equation for work that we'll talk about in a second, which is work is equal to force times distance times cosine of theta. But most of the time that's one.
Yeah, no, usually, yeah, and
Most
don't
of
get
the
me
time
started on
that's
the
one, so we
Don't get me
mostly
started on the
ignore it.
cosine side. I'll talk about the cosine signs later because I think there's a cool anyway. No, I'm not,
Yeah.
not right now.
So ball is on top of the hill. It's storing gravitational potential energy, which is essentially the force of gravity times how high up it is. Okay. If you push that ball from motion or from rest, where it's not storing any energy in its motion, it's not moving, it's just there, right? 100% gravitational potential energy. If I push that thing and it starts to roll down a hill, that energy is being lost. Because if potential energy is m times g times h, which is height is going down as I roll down the hill. Potential energy is, in quotes, being destroyed.
No, never. No, never, never. We can't do that.
Wait, but where does it go? Right? No. It's starting to move. It's just being converted to kinetic energy. And again, the ball down the hill is a pretty classic example. You have potential energy being converted to kinetic energy, which is the energy associated with movement. This is this is 1/2 m times v squared. Okay, it's the same units actually.
So joules.
Mass times velocity squared. Yeah, but it's being converted into movement. So
right. And this whole idea of conversion is really cool. That's because, again, can't be created or destroyed. And I love the idea of potential energy in general, because a lot of the times people just say, yes, it has potential energy, because people have usually heard like the ball on top of the hill. I always, my classical example was we just dropped the ball, like we was holding up, then we just dropped it, right? And then, but this idea of potential energy, I feel like a lot of students are like, okay, when do I have potential energy? Or is potential energy all the same? Now, my always idea with potential energy, this is a very simplified version of potential energy, but my always idea is if you let it go, does it move? That's my core potential energy. If you let it go, does it move? If you want to know if something has gravitational potential energy, let it go. If it moved, that means movement has kinetic energy, but I can't just create kinetic energy out of nowhere. Oh, it must have come from something. It must have been converted from potential energy. The reason this is important because the only potential energy isn't just gravitational potential energy. Even though that's the one that people are like, oh yeah, that's the potential energy. No, no, no. Potential energy is like ice cream. There's so many flavors, right? So there's gravitational potential energy, but there's also things like elastic potential energy, where imagine if I held a spring, right? If I let go, would it move? Then there must be.
Have you compressed the spring?
I have, yes, I've compressed it. Yes, I've compressed the spring. Yes,
yes,
you're right, you're right. Yes, yes, yes. I've compressed the spring. If I let go, does it move? Well, if there is movement, that means there's kinetic energy. Well, therefore, kinetic energy can't have come from nowhere because we can't create energy. Therefore, there must have been potential energy. And that was in the form of elastic potential energy, where the equation is a little similar to the force of the elastic force or the spring force, where it's instead of kx, it's kind of similar to the kinetic energy equation, but it's
the hybrid.
It's kind of a hybrid. It's 1/2 kx squared, right? So in the same way that kinetic energy was 1/2 mv squared, spring potential energy is 1/2 kx squared. But that's not the only flavor of potential energy that we see. We've got more flavors. Molly, what's some more energy flavors that we see in potential energy?
Energy flavors. Okay, I mean, there are so many that we could talk about. MCAT typically will give you 4. Okay, gravitational, we have elastic. We also have potential energy in things called capacitors. Now, we haven't talked a bunch about circuit elements here, but capacitors are circuit elements that can store energy by separating charge, right? That's the essential idea. Is you've got, in some cases, parallel plates. You've got a bunch of positives, a bunch of negatives right here, right close together, but they can't meet. They can't touch. They want to, right? If you connected those two poles of the capacitor, they would move. Okay, same criteria as you had before, right? They may not be able to move yet, but if they could, they would. Okay. So that is, again, a similar equation, and you'll start to recognize a lot of patterns. This one, potential energy of a capacitor, is 1/2.
So the 1/2, yeah. Yeah.
Yes, C, which is the capacitance, times V squared. Okay, and I just want to be super intentional because of kinetic energy that has a V squared. This is not velocity. This is voltage. And this comes down to something we were talking about last episode with MCAT math. It is not enough to know what the equation is. You need to know what the variables are, right? Because is that volume? Is that velocity? Is that voltage? You have to know what V means, right? In this case, it's 1/2 CV squared, and V is voltage, not velocity, like it is for kinetic energy. So that's important. We also can talk about electrostatics formulas.
Yeah,
Pretty related, right? But
sure.
the potential energy created when you have, let's say, a positive and a negative charge, or a positive and a positive. And electrostatics equations, if we wanted to talk about electrostatic potential energy, that would be a whole nother topic.
There's a whole nother episode just for that because it needs its own. But I mean, if
Yes.
we're talking about energy, we can't not talk about the electrostatic potential energy.
Mhm.
And to that example of positive to positive, yeah, we can imagine. Like I remember as a kid, like holding magnets together and being like, "Oh my goodness, if I let go, they move." I was like, "This is
Yeah.
crazy," because I couldn't see anything in between, right? But
Mhm.
as soon as I let go, it would move away. But wait a minute.
Mhm.
If I let go and then it moved, wait, it moved. Therefore, I had kinetic energy. Oh, therefore, while I was
Mhm.
holding it there, it must have had what?
Potential
It
energy.
must have, because we can't have created that kinetic energy from nowhere. So this is the electrostatic potential energy, where if I hold a
Mhm.
charge next to some sort of potential, there will be energy. That's where the equation that I like to talk about comes from, where it says U, which represent the electrostatic potential energy, equals Q, which represents charge, like the magnitude of the charge, times the voltage. Still V, not velocity, not volume. This is voltage. Charge times voltage is the electrostatic potential energy.
Hmm.
Hmm. Hmm.
Yeah. So lots of different flavors. I love that you get so passionate about that, because I get passionate about that too. People are like,
Hmm.
"Oh, potential energy equation, it's MGH." But wait,
Hmm.
I don't have mass and I don't know what the height is, because there's no object that's lifted to a height, because we're talking about springs, right? Like there are lots of different equations that we could use for that. So, yeah, very important. And again, the whole idea here is that energy is converted from one form to another. It's not created or destroyed. Okay. Think back to Mike's heat death of the universe.
I mean, you
I
can't
really
forget
love
it
Mike.
now. We got only to find an amount, and it'll run out, or not run out.
Oh
It'll
my
be
God.
converted to something we can't really use.
Yes, yes.
Mm.
And this brings us to our discussion of work. Okay.
Mm.
Because I feel like we talk a lot about energy and I think we intuitively understand it, but the question becomes, well, what if I have, let's say, a force that's changing something? I'm
Mm.
applying a force to something.
Mhm.
Let's say I am applying a force to an object. I get it to move and I push it over a distance.
Mhm.
What is happening? What are we
Interesting.
doing?
Interesting, because I would think, okay, if I have a brick, does it have, like, if it's on the ground, is there any potential energy there? Like a huge stone brick. If it's just on the ground, it's not moving,
I
it's just
my
sitting there.
brain is like, is it at sea level?
Is that yes? No,
Is it on the
our
ground in a plane?
our relative height is
Relative height is zero. Okay, no,
yeah.
no potential
Yes, yeah, I'm
energy.
not trying to trick you. Yeah, yeah. Block. But if it's just sitting there, is there even any kinetic energy though?
No.
No. But if I start pushing it, right, it's now
Hmm.
moving. So does it have
Hmm.
kinetic energy now?
It does now.
Oh, like, did we just create energy out of nowhere?
Yeah, no.
No,
No, of
no,
course
no, no,
not.
of course not.
Mike, come on.
We cannot violate it, right? But this work is the idea of energy transfer, right? Because we just
Hmm.
talked about like how energy can be converted to different forms. Like it can still stay in the same system, but we can also transfer energy between different objects. And this idea is what we call work. Work is the transfer of energy, right? And that's
Hmm.
why, right, we multiply and work, therefore it's a transfer energy. It's measured in joules, right?
Hmm.
Work is energy. It's just the transfer of it. And we see that in the equation for work, where it's
Hmm.
force, which is newtons, times distance, which is meters, times cos theta. So let's talk about the let's talk about the cos theta. Because this is an important idea I always like to illustrate. Say I am pushing a brick, like a big, so I'm, oh, when I say brick, I mean like my background's Egyptian. If
A
no,
boulder.
I think like the Egypt, you know, the Egyptian, like the pyramids of Giza. You know how they
Big
have those big
giant
stone
bricks.
bricks?
Yes, yes.
That's what I imagine when I think pushing a brick. So that's
Oh,
like
pushing like a tiny little brick.
no, that I'm pushing the real ones because I'm just like that. Anyway,
Okay.
so imagine if I'm pushing it, right? I'm applying a force and it's moving a displacement. But wait a minute, there's other forces on that brick, right? There's the
Hmm.
force of gravity on that
Gravity,
brick. The normal force is on that
friction.
brick. There's
Yes.
friction on that brick. But okay, wait a minute. Does the force of gravity is on that brick and it's going a distance? Is the force of gravity doing any work on the brick?
No.
No. But wait a minute, it's a force and it's going over distance. But this is the idea of work. the only forces that do work are the forces that are in the direction of motion or in the axes of motion. So I am pushing the brick, this giant brick, horizontally.
Mhm.
Anything that is in the horizontal plane is going to be doing work. But
Mhm.
anything in the vertical plane that is up or down, it is not in the direction of motion, so it does no work. There are forces, but if it's not in the direction of motion, it does no work. And this is why FD cos theta is really important. Because what if I'm not pushing exactly horizontally? What if I'm pushing a little bit upwards, like on a diagonal, right?
Yeah.
Right? If I'm pushing up on a diagonal, not all of my force is actually taking part in the work, right? If I'm pushing on a diagonal, I need to figure out which portion of my force is actually doing work. And this is where we break down forces because they are vectors into
Mhm.
components, right? And so we haven't talked too much about vectors, but vectors are just any value that has a magnitude and a direction. Now,
Mhm.
we a lot of times like always do our problems in the X and Y axis, like the horizontal plane and the vertical plane. But as soon as any vector becomes in any plane that's not X or Y, we can break it down into its X and Y components, its horizontal and vertical components. And when we do FD cos theta, what we're really doing is trying to find the component that's actually doing the work. And that's why if I'm pushing straight on, right? If I'm pushing straight on, the angle is 0, and the
To
cos of 0 is 1.
to clarify, we didn't officially say this. Theta is the angle between the force
Mhm.
and the displacement.
Yes, yes,
So
yes.
that's just in case anyone's like, wait, but what is
Is
theta?
theta. What is theta? Yeah, I always overlook that because I'm like, okay, let's talk about the components. No, here, I thank you for catching that. Yeah, the theta is that angle where I want to figure out how much of it's actually doing the work. And so when I think about this equation, I actually just think about it as FD because I'm like, oh yeah, just figure out the one that's doing the work. But that's why the cos theta is there to figure
Yeah.
out, well, if it's not exactly on the plane, what part of the force, what component of the force is actually doing the work, which I
And
think is cool.
I feel like it's really interesting to think of what, again, what theta means, because if force and displacement are in the same direction, your theta is 0.
Hmm.
Cosine of 0 is 1.
Right.
Okay. In your case, though, when we were talking about pushing the brick, which is a
Hmm.
big brick, not a
Brick,
little
not
brick,
a
we
little
got that.
one.
When you're doing that, think of the force of gravity. That is at a 90-degree angle to the displacement, right? That
Mhm.
force. Cosine of 90 is 0,
0.
which is why you don't consider it, right?
Hmm.
The inclined plane idea of like pushing it up a ramp of some sort is a really interesting
Mm.
application of this information. Again, inclined planes are one of those simple machines. And I feel like it brings in a really interesting discussion of forces and work, right? When we talk about conservative forces, right,
Mm.
versus non-conservative forces. So one of the things that makes, you know, let's imagine we have a gigantic brick, right?
Yeah,
We
we've been
have to,
working there.
I know, it's huge. We either have to get underneath it and lift it up 10 meters.
Oh wow.
Huh?
Oh
Okay,
wow.
even 10 centimeters.
Yeah.
That's hard.
Hmm.
That's really hard,
Hmm.
right?
Hmm.
My theta in that case, if I am applying a force, an upward force on it, and I'm displacing it up, my theta is 0. That's a lot of work that I have to apply, right? And the force is going to be very, very large in effect to lift it, even 10 centimeters. What if I could push it on a ramp? If I got it
Mm.
on a ramp, now it's a much, it feels easier to do that.
Hmm.
It feels much easier to do that. And actually, your force that you have to apply to it will be smaller.
Mm.
How does that work though? Right? Think
Mm.
about what you are doing to that giant boulder or to that giant brick. You're lifting it up 10 centimeters. One of the things that we need to be familiar with is gravity is
Hmm.
an example of what we call a conservative force. It means
Hmm.
it doesn't care how you got there.
Hmm.
It is what it is, right? If you took that brick and brought it down 10 centimeters and then up 30 centimeters and then down 20 centimeters and then over to the left and then back over here and then down and then up and then down and then up, if the net displacement was 10 centimeters, it's the same amount of work, right? Like
Exactly.
the energy expended is the same,
Exact
right?
same.
If you do this over an inclined plane, right? Again, the force feels easier to do, but it's the same amount of work, right? To push it up a ramp versus to lift it from below.
Right.
So if work is the same,
Mm-hmm.
how does this give you how does this make it any easier to push it up a ramp?
Right.
Right? The work is the same
Mhm.
joules
Yeah, but the force
required.
is less, and
The
work
force
equals
is
force
less.
times displacement. What is it? What could it be? Well, it's about how far did you move it, right? The
Mhm.
distance that you moved it, right? Before, you were just bringing up straight 10 centimeters. You're just bringing up 10 centimeters. It was a short distance. You had to generate a lot of
A lot
force.
of force.
Now we're kind of flipping it. Now, when imagine a ramp, like imagine like a really shallow ramp. Like to go over a certain height, it takes a lot of way, a lot of distance that you have to cover in order to get that same height. Well,
Yeah.
that's why the force is less because the displacement is far greater,
Yeah.
right? You have to do
So
a much larger distance.
imagine a ramp that's 10 centimeters tall, but
Yeah.
let's say it's a full meter long.
Yeah.
Like you have to push that gigantic brick a full meter just in order to rise it 10 centimeters. That's kind of what we're talking about,
Yeah.
right? Like think of like a wheelchair ramp, for
Hmm.
example. It's the
Hmm.
same amount of energy to pick a wheelchair up and move it and set it down on a step as it would be for that very long wheelchair ramp to raise that same
Hmm.
uh,
Height.
amount, right?
Yeah.
It's much easier to carry
Roll it up the
someone or
ramp. Yeah.
roll it up the ramp. That's even using wheels, which is another.
Well, we're not touching that. We're
We're
not
not
touching
touching that,
that.
but it's the same amount of work. It's just much easier to do because it requires a lower force
Mhm.
over a longer distance, right? So that's very interesting. And you'll notice a lot of the inclined planes problems that you'll see, they will use this particular term frictionless.
Mm.
They say it all the time. A frictionless inclined plane. Why does that matter? Right?
Mhm.
It's actually because where gravity was a conservative force, where you could really take any possible path, it just cares about where you end up and where you started.
Mhm.
Okay. That's
Mhm.
all that matters. There are non-conservative forces, which means the path that you take does matter.
Mhm.
Right. And friction is one of them. Right.
Mhm.
If I push something 1 meter versus 10, friction is going to create a very different amount of work required, right? So
Right.
that is a non-conservative force.
Right.
And that's why they'll specify, right? Because that could
Frictionless. Yeah.
change, yeah, that could change things for us on an inclined plane.
Yeah, friction's really, really cool because this is when we start talking about like energy in the system versus energy out of the system, right? Because like if I'm pushing like somebody across like, a really rocky surface, you would think, oh, like maybe over a rocky ramp, maybe there is friction, right? Now the energy required isn't just the height anymore because now the friction is
Mhm.
taking away energy out of my system because it's doing work, but it's doing
Mhm.
negative work, right? Because work is the transfer of energy. Normally we think of work, oh, I'm pushing the brick, so I'm putting energy into the brick. And now as kinetic energy, friction as a non-conservative force is taking energy out of the brick, right? That's
Mhm.
why, imagine if you kick a soccer ball on like something rocky, right? If I kick it, I gave it energy. I did work to the ball, right? I
Mhm.
applied a large force over a short distance, right? But if it's rolling on the grass, there is friction there. So the grass is taking the energy out of the ball. This is why
Yeah.
the ball will eventually stop. In the
Yeah.
same way, when I throw something in the air, like so
Yeah.
air resistance is also a non-conservative. It's kind of like an air friction that you can think about. Like that's what air resistance kind of is, just the air molecules. When you throw something, it slows down midair because the non-conservative force of air resistance is taking energy out of the system, out of the ball. So this is why friction matters when we talk about, oh, is it frictionless? Is it not frictionless? Because if it is friction, yes, it's doing work in the opposite direction. It is taking energy out. That's why the problem becomes, I think, much simpler when it's frictionless. So you don't have to just worry about
Yes.
friction. So
Yes.
normally that's why they do have to specify. It is important if they say friction or no friction.
Yes.
Mm-hmm.
Yeah. And there's lots of interesting ways that they can ask you to apply this information mathematically. Again, we always say make sure to get practice, but especially with this material, and
Yes.
especially since our last episode was about math, go get lots of practice.
Time to
Right.
apply those skills, right?
Time to apply those skills. And I feel like we've got one last thing to talk about. And I feel like it's interesting to consider a hypothetical. Okay.
Sure.
So let's think about this.
Mm.
hypothetical situation.
I'm with you.
We need to run.
I hate this already.
I know, I know, I know.
I want to end the
I'm saying it
hypothetical.
gently. Neither of us are good runners, right? But
Not at
let's
all.
imagine that we have to traverse a mile.
Okay.
Okay. You have to either jog a mile
Okay.
or sprint a mile.
Oh my goodness. Okay.
Okay. Which one requires more energy?
Interesting. Wait a minute. It's the same distance,
It's
right?
the same distance.
And I don't, and it's the same weight in both cases, so it's the same force. So I would think it would probably be the same exact energy.
So why is it easier to jog than sprint? And honestly, jogging is hard too. Walking a mile would be the same thing. Why is walking a mile easier than sprinting if it
If it's the
requires the
same
same energy?
energy. Hmm. I guess time has a factor here, doesn't it?
How fast you go changes
Yeah.
everything.
Yeah.
That's what brings the misery of a sprint,
Hmm.
right? Although it's excellent cardio. Yes, this leads us to our last topic for today, which is actually pretty short and sweet, to be honest with you, which is power, right? The whole idea of walking or jogging or sprinting, yeah, it's the same displacement, right? And
Hmm.
you're opposing the same force.
Hmm.
Why then is it feel easier and not as awful to walk than sprint? It's because of how fast you have to expend that same amount of energy.
Hmm.
Okay. So the whole idea is it requires a higher power
Hmm.
to sprint than to jog or to walk.
Hmm.
Okay. And this brings us to our final equation for today and our
Hmm.
final unit, which is power is equal to work, which again is energy transfer. So it's in joules, divided by time. Okay. Which is in seconds. So if we track the units, we knew from force is mass times acceleration, right? Force is kilograms times meters over second squared, right? We're happy with that. We then took that and made work, which was kilograms times meters divided by second squared times meters,
Hmm.
right? So we were a Newton meter. So we were
Hmm.
kilograms times meters squared over second squared.
Yes.
Now we're doing all of that, but divided by time.
Love that.
Right? So it's a Newton meter divided by a second,
Wait
or
a
a
minute.
joule divided by a second.
Wait, you just say Newton meter over seconds?
Mm-hmm.
Wait a minute. Meters per second. That reminds me of something.
Oh, what is meters per second? It
Wait a
sounds
minute.
like one of
Velocity,
our V's.
right?
Volume.
Oh,
Oh,
one of
velocity.
the, not volume.
Voltage?
No, velocity. Wait, so it's newtons times meters over seconds, which we can say is a watt, which is the unit of power, but that means it's the same as newtons times meters per second, which is force times
Velocity.
velocity. So power is not only equal to work over time, but it's also equal to force times velocity as well.
Yes.
Hmm.
Yes, exactly. And that is something that I feel like I don't often see equation sheets list power is equal to force times velocity, but I've seen it a fair amount in the questions.
Right.
Like, and it's kind of intuitive. They want to see if you could troubleshoot. I feel like they know that it's not often taught directly. In some cases it is, in which case, nice. But
Hmm.
a lot of people don't report ever hearing power is equal to force times velocity, but
Hmm.
it's the same equation. If
Hmm.
work, we're assuming it's FD times cosine
Right.
theta, which is usually one.
Hmm.
FD divided by time,
Hmm.
it is force times velocity.
Hmm.
Um, so keep an eye out, right? This is why we focus on units and we focus on understanding how equations are connected because they could give you force and velocity and ask to calculate power. And if all you know is work over time, you might feel stuck,
Right.
right? See what you have, see what you're given. In that case, okay, what do you know about power? It's work over time. I have force and velocity. Can I make one of these things force or velocity? I would see work and say, well, that's F times D. Now I at
Hmm.
least have one of the things that I uh in my equation, right? I have distance over time. Wait a minute, that's my other thing, right? They
Velocity,
use
right?
problem solving like that a lot with these
Hmm.
questions.
Hmm. And that's why applying the skills we talked about last episode with MCAT math when we have problems like these, because that's why physics is so great. Because it's not enough to just know the content. You can't just like listen to this and now you're proficient at physics. You can't, oh, now you're a master of physics. No, you have to apply it, where you now combine those conceptual skills with the problem solving skills and the systems that we learned about in MCAT math. So that's why physics is so cool, because you put those two things together in order to answer problems. You can't just do like one or the other, which sometimes that's why it's a little bit difficult, because it kind of flexes a muscle that we're not used to flexing maybe as hard in other subjects.
Yes, for sure. And honestly, I feel like this is one part of the puzzle with chemistry and physics, right? Obviously, there's a whole nother ball game when we talk about OChem and Gen Chem, but like physics in particular gives us a lot of very unique challenges that are not present in undergrad the same way, or present in other sections the same way, right? And for this reason, this kind of leads into our topic for next episode. Right? We are going to start a new little mini series. We're going to talk about how to master each section individually. Okay, we've talked about how to master MCAT passages in general. We talked about MCAT questions in general. We talked about math. And now we're kind of talking about content that's very foundational to these subjects, but we want to put it all together. Okay, so our next episode, we're going to be talking about how to master the chemistry and physics section. So what makes ChemPhys passages different from our generic passage strategies that we talked about? How do we tweak those, or how do we adjust those in order to succeed in this section in particular? I'm very excited for this little series. We will do biochem and psych soc as well. How do we tweak this general approach that we've shared to make ChemPhys easier than it is for us right now? And again, biochem and psych soc
are coming after. Yeah. And if you're
not to spoil it,
not to spoil it. Oh my goodness. But yeah, if you're wondering about like what do you mean by this general strategy, a few episodes we did an episode on how to tackle science passages in general. Highly recommend giving that a watch. Or giving that a listen, or depending on how you consume this content, to kind of go through like, oh, how are we reading science passages? And then we're going to be using those same skills. Like, we're not changing any of them completely, but tweaking them in order to tailor them to the different sections. Because what we find a lot of the times is some students have the same science strategy but struggle with certain sections over the others. So maybe we have to, if you find that, oh, I'm great on bio, but ChemPhys gives me a little bit of difficulty with those passages, we'll talk about how to tweak the strategy to make it, much more doable for you. So if you haven't given that last episode a listen, take a listen to it, and I'm also looking forward to the next one as well.
Yes, it should be fun. We hope you've enjoyed this episode, and I hope you guys are getting stoked for our next one. Until then, have a wonderful rest of your day or week or month or whenever. And we will catch you in the next one.
Happy studying, everyone. Bye now. Welcome to the Jack Westin MCAT podcast with your hosts, Michael Maleka
and Molly Hudash.